conference together. So let's start. So hi, my name is James Mickens. I'm from Microsoft Research in Seattle. And today I'm going to talk to you about several cool projects that we've been doing in the web space. And at a high level, all of these projects essentially investigate ways to make web pages run faster and more robustly on today's commodity, unmodified browsers. Before I continue, let me just give you a quick overview of what this talk is and what it isn't. So what this talk is a discussion of basic research that's going to benefit many different web pages running on a variety of unmodified browsers. Now, here's what the talk isn't. So this isn't an opportunity for me to get up here and evangelize about particular Microsoft products or try to get trapped in browser wars about this is better than the other. This research is going to benefit a lot of different browsers running a lot of different pages. Furthermore, I'm up here, I'm describing research prototypes. So I'm not going to talk about some shrink wrap product you can go out and get right now. This stuff is very much still just research stuff, but we'd love to hear your feedback. Please do ask questions or catch me in my demo session that I'll have tomorrow. So, with that out of the way, let's begin the real talk. The internet. People love it. It is, of course, a series of tubes. And one of the things that people do on those tubes is surf the web, right? Use web applications. Now, as web developers, a key challenge is to make these web pages as fast and as feature-rich as desktop applications. However, there are a lot of challenges to realizing that vision. And today I'm going to talk about two of those challenges in particular. The first challenge is that the network is often slow, but users are always impatient. Empirical research shows that half of users will abandon a web application that takes more than 2 or 3 seconds to load. So making these pages load quickly is extremely important. However, as developers, we want to include a lot of JavaScript, a lot of CSS, a lot of resources in the page, and that can take a long time to download if the network is slow. So a lot of my research has looked at different ways to allow web pages to use the network more efficiently. Now, the second challenge is that web applications are often breaking. So if you're a huge dork like me and you surf the web with your JavaScript console open, then you'll see that you're constantly seeing JavaScript errors, uncaught exceptions, variables not found, all kinds of things like that. And even if there aren't these types of problems, oftentimes web pages just don't do what we want them to do. I might move my mouse over a flyout menu, nothing flies out. I might hit, next picture on a photo album, and nothing shows up. And so another big chunk of my research has looked at different ways to allow web developers to make more robust web programs. And so the key insight behind all the research I'm going to talk to you about today is that JavaScript turns web browsers into first-class computational entities. And in particular, JavaScript allows web programs to be so powerful that we can take a lot of cool research ideas from the world of traditional operating systems or networking research, and this was research that was intended for desktop applications, and we can start applying some of that towards web programs. And so in this talk, I'm going to talk to you about 2 specific projects. The first project is called Silo, and basically we're going to use some neat tricks with JavaScript and DOM storage to layer a custom Delta encoding protocol atop HTTP. And I'll show you results that demonstrate that in some cases, Silo can reduce the load time of web pages by more than 40 or 50%. The second project that I'm going to talk to you about today is called Footprints, and this is about logging and replaying buggy web applications. Effectively, what we're going to do is we're going to log all the non-determinism that takes place on the client side of the web application. Then when your web app breaks, you can actually send that log back to the developer who can then replay your buggy application. So I'm going to go into much more depth about these things in a second. Before I do, I just want to say all of these projects work in unmodified browsers. That's extremely important from the perspective of deployability. Nothing I'm going to show you today requires a special plugin. You don't have to run your browser in a VM, anything like that. Okay? Basically what I'm doing is taking advantage of the rich power of introspection and reflection that JavaScript provides to pull off some pretty cool tricks. So let's first talk about Silo. So what happens when you want to actually load a web page? Well, your web browser is going to send a GET request to the web server. Then that web server is going to send back some HTML. Now, as your browser parses that HTML, it's going to find references to externally named objects like this a.cs. So your browser will send out a fetch request for that, and then eventually the browser is going to send out more requests to the server, and the sending out of these requests and the response by the server happens somewhat in parallel, but not completely in parallel. So the thing to note here is that we're actually spending a lot of round trips to fetch all of this data, right? Why is that a problem? Well, that makes pages load slowly, and this makes users sleepy and or unhappy. Of course, we want to avoid that kind of thing. So, what am I telling you? Well, I'm telling you that RTTs are considered harmful. I'm not a super genius. This observation has been made before, right? So web developers already know this. But there are not a whole lot of satisfactory ways to deal with this notion of eliminating RTTs. So let's discuss some of those options. So let's say that you've got some rich page like ESPN.com, you've got a lot of JavaScript, a lot of CSS to make things cool and nice and interactive. Well, you might think that one way you can reduce the number of RTTs needed to build that page is simply to just use fewer JavaScript and CSS files, right? Just leave some of them out. Now, the problem with this, of course, is that the more and more JavaScript and CS files you remove, the more and more your web page is about as fun as a children's game, Ball and Cup. And, of course, nobody likes the old children's game, Ball and Cup. So in practice, nobody uses this approach. No one's just going to gut all of their CSS and JavaScript just to make their page load faster. So another technique you can use is as follows. Let's say that you've got your web page up there, that's the HTML, and you've got some externally named object, like let's say a.js. So one thing that you can do is you can aggressively inline all your JavaScript and CSS. So now, instead of having an external link, you just take the source code of that JavaScript file and just put it straight in the HTML. What's nice about this is that you haven't sacrificed any of the functionality of the page, but you're avoiding that RTT to get that object. Well, what's the problem with that? Well, now your browser cache is useless, right? Because you've got this huge inline page, and you only needed one RTT to fetch it. But now if any single byte changes in that inline page, the whole thing has to be refetched, right? And the browser cache only understands objects named at the granularity of a URL. Right? So now your browser cache doesn't know about a.js. So if one thing changes, the whole page has to be destroyed. So here's a high-level overview of what Silo is going to do. It's basically a delta encoding protocol atop HTTP. So in Silo, you're going to send the request for the page, ESPN.com or whatever, as before. But the web server, instead of returning HTML, is going to return a small JavaScript shim, which is going to check the local chunk database, which uses DOM storage, as I'll discuss later. And it's going to say what chunks in that page are locally resident. So it's going to send those local chunk IDs to the web server, and then the web server is going to respond with the chunk IDs, or the raw data, in the inline page, right, with inline JavaScript, CSS, stuff like that. So it's going to send back those chunk IDs, and it's also going to say, hey, here's the raw data for the chunks that you don't have locally. And so what the web client's going to do in that JavaScript shim, it's going to assemble all the chunks, either the ones that were available locally or that came from the server. It's going to overwrite the page, and then store any new chunks that came from the server. So what's the advantage of this? Well, there's a couple of advantages. First of all, using this technique, we can fetch an arbitrary number of JavaScript and CSS files in only 2 HTTP round trips, right, without reducing the number of objects. So that avoids the ball and cup syndrome. And I'll actually show you how we can get down to actually 1 RTT to fetch all this stuff. Second of all, caching is restored. And in fact, caching is finer grained because DOM storage allows JavaScript files to explicitly interact with this stable storage, right? And here, of course, I represent caching by the Hamburglar, who is known for opportunistically caching other people's hamburgers. The third advantage of this is that you don't have to change your hair or your browser to get all this to work, right? So DOM storage is already part of the HTML5 spec. It's in Firefox, it's in IE, it's in a bunch of different other browsers. So this all works on regular systems. The end client doesn't have to be changed at all. So here's an outline of the rest of the talk. I'll give you a brief overview of delta encoding in JavaScript. I'll go into more depth about the Silo protocol, and then give you a couple slides of evaluation. So crash primer on delta encoding. So you've got 2 people, Alice and Bob. They want to share an object. So let's say Alice generates the object, and for the first version of the object, she has to ship all the bytes over to Bob. Now let's say that Alice changes the object. Well, in the naive scheme, to tell Bob about the update, she has to ship the whole object over to Bob. And this can be inefficient. So delta encoding does the following. So Alice first generates the object, sends that initial version over to Bob in its entirety. But then when Alice creates a new version of the object, she compares it to the old version and says, here are the diffs or the deltas that would transform the original object into the new one. And she only sends those diffs over to Bob, so that Bob can now take those diffs, apply to the original object, and recreate Alice's new object without having to have the entire object transmitted to him. So one very convenient way to do delta encoding is using this technique called Rabin fingerprints. So say we've got this object here that we want to delta encode. So what we do is we take a sliding window, a small sliding window of, let's say, 48 bytes, and we slide it across the object. And at every point as we slide, we calculate a fingerprint, essentially just a hash function of the bytes that are in that window. And so what we do is that as we slide the window across the object, we declare a chunk boundary whenever the lower order bytes of that fingerprint are 0. So in this case, whenever the lower order byte is 0, we decide to put a chunk boundary there. And so we continue to slide the window across the object, creating chunk boundaries as I just showed you. And then for each one of ththese chunks, we typically name it by its hash, SHA-1, MD5, whatever. And the nice thing about this scheme is that two parties can independently take the same object and generate the same chunks without having to communicate. And furthermore, if we make a change to the object in the middle of the object, then we may change the chunks that are immediately surrounding that edit, but all chunks further than that are not changed at all. So what kind of stuff can we chunk in a web page? Well, there are 4 basic categories of web data. There's HTML, there's CSS, JavaScript, multimedia stuff. Suffice it to say that the first 3 types of things are amenable to delta encoding because they're textual-based content that basically changes in sort of reasonable-sized diffs. Multimedia files like movies, typically it just changes sort of wholesale, so it's not really amenable to this delta encoding idea. So cool. Hopefully everybody's on board here, right? Everybody seems like chunking seems like a good idea. Now, can't we just put this in regular browsers now? Well, with apologies to the classic 80s movie The Goonies, not everybody loves chunks, right? Why is that? Well, once again, the browser does not expose an explicit interface to the cache to JavaScript. So it's not like JavaScript can just create some chunks and then read and write the cache as it wants willy-nilly, right? So we're going to have to actually use this DOM storage stuff I've been talking about to actually get all this stuff to work. So here's a crash course in the 4 features of JavaScript that I'm going to use to actually make all this stuff work, right? So the first feature I'm going to use is this DOM storage. And you can just think of DOM storage as a very simple key-value pair database that's exposed to each web domain. It's sort of its private database. The second feature I'm going to use is the AJAX facility to asynchronously fetch data. I'm sure you're all very familiar with that. I'm going to use document.write calls to actually overwrite a page's content dynamically. And I'm also going to use cookies, as I'll show you in a second. So let me go into more depth about the Silo protocol. So in Silo, the browser is going to send a request for some page, foo.com. The web server is going to respond back with this JavaScript shim. So what is this shim going to do? Well, inside the script code, we see that the server automatically inserts the IDs of the chunks that are in the inline page. Okay? So the shim is then going to look in DOM storage, and it's going to say, OK, which one of these chunks do I not have available locally? It's going to send a synchronous AJAX request to the web server saying, hey, can you send me those missing chunks? It's going to get those missing chunks back, and then it's going to use document.write to overwrite the page. So that's pretty cool. That's all that it is. It's actually not that complicated, right? So using that simple protocol, I've actually fetched an arbitrary number of HTML, JavaScript, and CSS in 2 round trips, right? However, like Mississippi's literacy program, I can actually do much better, right? So what I'm going to show you now is I'm going to show you how we can use cookies to actually get rid of an entire round trip, which is half the round trips we're using right now, i.e. down to 1. So very crash course on HTTP cookies. Cookies are little files that are associated with each web page. When you send a request for a web page, say foo.com, your browser automatically sends any cookie that's available with it. The web server can look at the cookie. It can send you back your page in addition to like a modified cookie. And then JavaScript can actually take that modified cookie and modify it further. So here's an optimized Silo protocol for when the cache is cold. For example, when the client hasn't visited the web page at all. So what happens here is that you issue the request, and you either don't have a cookie because you've never been there, or for whatever reason, maybe your DOM storage got cleared. You do have a cookie, but you say that the cache is cold. And so here's what the server returns. It actually sends something that we call annotated HTML. Okay? So what's in this annotated HTML? Well, first of all, it's the inline HTML, CSS, and JavaScript. And the reason why we send back the inline stuff now is because the client can just commit this annotated HTML immediately without doing any synchronous JavaScript operations to chunk the page or whatever. So it can immediately chunk this inline HTML, CSS, and JavaScript. Now, at the end of that inline file, we actually have the Silo code that's going to extract the chunks, update the cookie, and do all this kind of stuff. And note that in this HTML comment, at the end of the annotated HTML, that's where we have the chunk ID, the SID, the offset within the annotated HTML when that chunk begins, and then the length of that chunk. Okay? So what's nice about this is that if the client cache is cold, we still fetch all the data in one HTTP round trip, and we can actually do the chunking operations asynchronously in the background. So here's an optimization for when the chunk cache is actually warm. The user has visited the page before. So this time, the user requests the page, and in the cookie, it says, hey, I actually have a warm cache, and here are the chunks that are locally available on the client machine, right? This is very convenient for the server, because now the server can send back a shim, which basically just does what I showed you before. So it's going to say, hey, here are all the chunks that are in the page. Here's all of the raw data for the chunks that are not locally available. And then the shim is just going to overwrite the current page content with document.write, update the local chunk cache, and then finally it's going to update the cookie, right? And that's basically that. Sweet. So what I've shown you is that using cookies, we can now fetch all of the pages, HTML, CSS, and JavaScript in one HTTP round trip, right? Now, a lesser man might just stop there and let you throw roses at me. I'm not that man, however. So what I'm going to do is now give you some evaluation results, which are going to show you when exactly Silo can and cannot help you, right? And that's what this slide says, evaluation. So here's the methodology that we use to evaluate this system. So to gather real web data, first of all, we took an unmodified client browser, but then we put it atop a special logging proxy so that whenever the client issued a request for, let's say, CNN.com, when that content came back, that content actually went to the browser, but also we saved a copy of it in the local proxies database. So then we want to simulate what a silo deployment will look like. We actually took that proxy, we put it out in the cloud, okay, and we turned the proxy into replay mode. And so we connected the browser to the cloud through a network link that basically simulated maybe like a mid-range DSL setup, 800 kilobits per second, about 150 milliseconds round trip. And so in the simulated silo deployment, when the browser asks for a particular web page, it goes to the proxy. That proxy is going to perform the inlining like a real Silo web server would, and then it's going to send that inline page back in the case of a cold cache scenario, or it's going to do that slightly more complicated warm cache protocol like I just described to you. So one question you might be asking is there enough chunkable content out there for this to make a difference? Right? Because you might be under the impression that, hey, isn't everything movies and sound files and stuff like that? And so what this graph here is showing you is that for several popular websites, we look on the y-axis, that's the number of objects in that website, and we break it down by CSS, JavaScript, and HTML, that is to say chunkable content, and then other, that's the blue bar, stuff that we can't chunk basically. And what we see is that for a lot of web pages, there's more than 20% of the objects are actually of the chunkable variety. And in fact, if you look at sites like, let's say, CNN or New York Times or Microsoft homepage, I mean, it's more than 35% in many cases. Now, the real sort of kicker is, does this result in a decrease in page load time? And so that's what this graph here is showing. Now, I give two definitions of load time here. The first definition of load time is DOM content loaded. And that's sort of the Firefox nomenclature. And what that means is DOM content loaded fires when you have all the pages HTML, CSS, and JavaScript. And that's essentially the earliest time at which a page can be usable, right? Because all the event handlers are there and all the basic layouts done. Now I also give numbers up here for the standard load event. Right? The standard load event can be a bit misleading because this waits for things like images to show up, and oftentimes these are served from third-party servers, and so load time may or may not be representative of the time that your page really feels like it's loaded to the user. But I give those numbers up here for completeness. And so what do we see? Well, we see that in some cases Silo doesn't really provide that much benefit. So maybe 5 to 10%. But we see that in some other cases, right, we see a very dramatic decrease in page load times regardless of what your metric is. So sites like BBC, sites like CNN, IMDb, if you look at, let's say, pure load time, traditionally defined, you can see improvements of anywhere from 25 to, let's say, 40%. If you look at DOM content loaded time, you can see improvements anywhere up to about 85% or so. And so what we think is that, in the worst case, we're actually not doing a lot of harm. Right? Like in the case of Twitter, Twitter is so simple and has so little JavaScript and CSS in the critical path for loading that the JavaScript chunking operations, basically the string operations, they slow things down just because they're computationally intensive. Right? But in the worst case, we're really not doing that much harm. And for a site like Twitter, you just wouldn't use this in the first place. Right? But what we see is that for sites that do have a lot of content that can be chunked, you actually see this really big win. So we're pretty excited about that. Now the next question is, what does load time look like in the warm cache scenario? So here we see that the benefits are much more muted, right? So typically, in the best case, you may only see improvements of, let's say, 10 to about 15%. But this actually isn't that surprising because Silo isn't really designed to help that much in cases where the cache is warm. And let me show you why. So in this graph here, we have Silo's benefit up on the y-axis, and then on the other axes, we see the degree to which the cache is cold and the degree to which there are a lot of objects on the synchronous load path for the page. And so essentially, Silo's benefit comes in this part of the graph to the right. right? The colder the cache is and the more objects you have to load to get that page ready, that's when Silo provides the biggest benefit, right? Because essentially what Silo does is it masks RTT latency. So if the cache is cold and there are a lot of objects, that's when we help out a lot. Now in the case where the cache is warm or there actually just aren't that many objects you have to fetch to build the page, we don't help that much, right? But as I showed before, we don't hurt that much either. And as many as you probably already know, the trend in current websites is not towards fewer and fewer JavaScript and CSS files. So we're not too concerned about this. And furthermore, empirical research shows that basically 40 to 60% of your visitors to a web page will actually have a totally empty cache. So we actually think that these numbers are actually pretty encouraging. So in summary, slow loading pages lead to anger, depression, and other societally undesirable outcomes. So you don't just want to reduce the number of objects in your page. This results in ball and cup syndrome. You also don't want to inline everything because then your browser cache becomes useless. So what Silo does is use JavaScript and DOM storage to aggressively inline all of your textual content. And then we use the DOM storage as an explicit cache that allows us to both aggressively inline stuff and actually restore the benefits of cacheability. So that's the Silo project, and we can take questions about that afterwards. But now I just want to switch gears a little bit and then talk about this Footprints project. And this is work that I did with some collaborators at Microsoft, Jeremy and John. So I don't have to sell this crowd that JavaScript is everywhere, web applications use it a lot, anything you click is probably going to trigger some stuff, blah, blah, blah. We all know this. So what's the problem with this? Well, the problem is that now when your web applications break, there's some kind of, oftentimes, JavaScript dependency, which is probably pretty opaque to you as an end user. So what kinds of problems might you encounter? Well, one type of problem you might encounter is so-called hard errors. So an unexpected exception is thrown by your code. There's some missing resource that your stuff can't find, something like this. This is the sort of canonical thing that I see when I surf the web. I mean, for some reason, we as society have become comfortable to our web programs throwing constant exceptions. This, I think, we can do better than. So there's those kinds of errors. Then there's quote-unquote soft errors. Maybe there's a layout glitch in your page. Maybe there's a broken event handler. You click something should happen, but nothing is happening. Or maybe you just have poor performance, right? So long story short, regardless of the type of error that you have, all these things lead the user to hulk out and become angry. We want to try to avoid those kinds of things. So you might be saying, isn't there already a lot of sort of best practices in dealing with errors in recovery? Well, you may be familiar with the Microsoft Customer Improvement Program, things like this. I mean, we have postmortems like core dumps, like stack traces, like error logs. Why can't we just do something like that for the web? Well, the reason I'd say is because JavaScript programs and web applications in general are very event-driven. And in event-driven systems, the event interleaving is key. So we don't just want a static snapshot of what the application looked like when it failed. We want the stairway to failure. We actually want to see the paths, the things that the user did and clicked on and downloaded and all that kind of stuff. We want to see that stuff, okay, not just a static snapshot. And furthermore, we cannot rely on the user to report non-deterministic events. There are two reasons for this. First of all, the user simply won't remember everything that he or she did. If you've read a human-generated bug report, you know how frustrating this can be. And second of all, let's even suppose that the user had perfect recall for everything that they did. They can't actually see anything, right, unless they're Neo from the Matrix, right? Like the user isn't going to see the return value of math.random. The user isn't going to see what date actually returned, how many milliseconds. The user isn't going to see when particular AJAX callbacks are fired, right? So the user is not the answer here, right? So here's what we do. So we come up with this tool called Footprints, and what it does is that it logs all the non-deterministic JavaScript events that take place on the client. Things like mouse clicks, things like date requests, things like random number generation. I'll go into this in more detail in a second. But essentially, we log all that non-deterministic activity on the client side, and then when something goes wrong, the user can essentially hit a panic button, right? And that panic button is going to send that log back to the web developer. And what the developer can do is take that log in the source code for the web application and essentially replay the user's buggy application run, right? The developer can single step, can go through in near real time. The developer can use all the sort of rich localhost debugging tools that we have, things like IE's built-in debugger, things like Firebug, all this kind of stuff. But the developer can use those rich tools on actual buggy application runs taken in from the wild. And so we think that footprints is awesome for 3 reasons. First of all, it's very easy to deploy to end users. Our logging and replay infrastructure is just a JavaScript library. Okay? So to first approximation, you ship the footprint infrastructure with your code just by putting our script tag first in your frame. That's basically it. Right? And importantly, you don't need a special kernel to run atop. You don't need a virtual machine. You don't need a plugin for your browser. So we think the deployability story here is actually pretty compelling. Second of all, the logging is lightweight enough that you can actually run it in the common case. So I'll give you some evaluation results later that show that in the worst case, the log growth is 16 kilobits per second. And that the CPU overhead for a very high-performance JavaScript game is at worst a 7% reduction in frame rate. And we actually found that that reduction was not perceivable by a regular user. And finally, we think that footprints is cool because it actually solves an important practical problem. As I'm sure many of you already know, it's very difficult to do bug repro for these web apps. So I think this is a pretty sort of practical problem and sort of a practical solution. So here's the outline for this part of the talk. First, let us go into the nitty-gritty of how the logging works. Then I'll just give you a brief overview of how the replay works. And then I'll give you some evaluation slides to show that it's low overhead. And once again, let me just plug the demo. I'll be having a demo tomorrow for the Footprints project. I encourage you to stop by and actually see a live run for how the log and the replay works. So here will be our example web page we'll be using to step through. As you can see, the web page consists of 2 horrifically colored frames, one green, one of which I don't even know that color. So what happens when the browser is going to parse the HTML for this page? So it's going to look to the tags, and then it's going to find this logging.js. As I said, to make your web page footprints compatible, you have to put that logging tag as the first script tag in your HTML. Now, that logging.js is going to do 2 things. First of all, it's going to interpose on all the sources of non-determinism in the page in ways that I'll describe to you in a second. Second of all, it's going to create an event log. This is basically where all of our events are going to go, and this will be used once the user actually starts interacting with the page. The browser continues to parse the HTML. We're going to come into that second inner iframe. The thing to note here is that each iframe is essentially its own JavaScript universe. Right? So every iframe that your application has to have a copy of our logging infrastructure in there too. Once again, the logging infrastructure is going to interpose on all the sources of non-determinism in the frame, and then it's going to say, hey, I'm a child frame. When I log all my events, let me send those events up to the event log in my parent. Then we're going to continue parsing the page, and then that's it. Now note that the on-click event handler, what does that do? So it's a very simple, kind of stupid event handler. It's just going to say, when you click on this button, then create a timeout callback, and that timeout is simply going to pop up an alert box with the current date in it. Right? Very simple. So let's say we've got this web page all rigged up and ready to go. So what happens when the user actually clicks on that button? Well, we have this timeout, this on-click handler here, and note that there are 3 sources of non-determinism that we need to log here. There's the mouse click itself. We need to log things like what button was used to click, what's the X and Y coordinates of the click, stuff like that. We need to log the callback, right? When does the browser actually fire that callback? And also, what function is it, the function ID, what callback was actually invoked? And finally, we need to log the non-deterministic value that's returned by date. So let's look at each of those 3 types of non-determinism and see how Footprints is able to log those things. So logging date calls is very straightforward. It works exactly the way that you think that it would. And we take advantage here of the fact that JavaScript allows you to do a lot of shimming or interposing upon native properties. So what we do is we just say, OK, we're going to get a reference to the old date function, save it in the variable old date. Then we're going to define a new date function, which essentially calls the underlying date to get the real value of date. It's going to log that event. Then it's just going to return that real date value back to the user. Okay, so that's very straightforward, works exactly the way that you think it should work. So how do you log set timeout? So it should be easy, but that easy is derision quotes, right? Because it's actually much more tricky than it should have been. So at a high level, all you have to do to interpose on set timeout is the following. So much like in date, we get a reference, we save a reference, to the original underlying set timeout function. Then we create a new wrapping version that's going to take in f, which is the application provided function, and the number of milliseconds to wait before that function is invoked. and we're going to take that user-specified function, we're going to assign it an integer callback ID, right? This is so that when we log it, we can say, hey, this is the function that we know at replay time we should actually invoke. Then we're going to take that user-specified wrap function, we're going to take that user-specified function, and we're going to wrap it in a callback that, when executed by the browser, is first going to log the fact, hey, this is the callback that was executed. Then it's actually going to invoke that application-provided callback. And then finally, what we're going to do is use the old setTimeout version, the one we didn't wrap, and actually register our wrapped application-provided callback with that old setTimeout function, right? Such that when the browser does actually invoke the application-provided callback, it calls our wrapped version. So that all seems relatively straightforward, right? Sadly, this does not work at all. And so basically, once I started working on this project, I thought everything was going to be like date, so I started with date, and I felt like, oh, I could get an intern to do this. This is like really easy. I'm like a super hacksaw. And like basically, I was just broken. I mean, it was just so bad. And as you all know, when you try to use some of these advanced JavaScript features, DOM prototype extension, or even some of the interposition stuff, things can break in really interesting ways. So why did it break in this case? So let's look at what we tried to do. So what we tried to do is save a reference to the original setTimeout function and then call it inside our wrapped version. Well, what we found is that the browser will garbage collect the reference to the original setTimeout, such that when we try to call old setTimeout inside of our wrapped version, it's going to fail. And the browser is going to say undefined function. Now, you might be saying to yourself, why is the browser garbage collecting this reference? Isn't this anti-garbage collection? Haven't you indeed saved a reference to something? Where is it going? Answer, you'd be correct, right? But this happens on Firefox, this happens on IE, this happens on Safari. It's messed up, right? And one of the reasons why these things happen is because JavaScript gives you a lot of power to do things like interpose and all kinds of tricks like that. But what happens is that there's basically two worlds. There's sort of the world that you see as the JavaScript programmer, then there's the C++ world in the browser beneath the scenes. And sometimes when you interpose on stuff, those worlds sort of get unhappy, and then you basically get the equivalent of a civil war inside your browser. So long story short, this sort of naive approach towards stuff doesn't quite work. So what did I end up having to do to get this to work? So the solution was for me to create an invisible iframe. This, of course, is a very popular hack that many web developers use. And it's sad, but this is the world that we've been given. So what I do is I create an invisible iframe, and I save its reference to setTimeout, right? And I invoke that iframe's original unwrapped setTimeout inside the wrap callback I was just telling you, right? It's dirty. I took a shower afterwards, but this is what you have to do, right? So let's just have a little recap here of the technical challenges here. So logging the date was easy. If that's all you wanted to do, just log date, man, you'd be doing great. Logging setTimeout should have been easy, but in fact was just a horrendous adventure of self-discovery and exploration. Now, if you'll remember, there was another piece of non-determinism that we had to log in that event handler example, right? It was the mouse click, right? Well, what about the mouse click? How do I do that? It's so bad I don't even feel comfortable describing to people I don't know, right? At a high level, let me give you a brief overview of why it was so horrendous. Right? So, and I'll give you two case studies, right? One on Firefox, one on IE. Like I said, this is not a platform for me to advocate for different browsers, other than the fact that they're all horrendous, right? So let's look at Firefox. Why was it tough on Firefox? Well, it's tough on Firefox because, well, let's think about this. If I want to log all the GUI inputs to a page, well, it seems like what I should be able to do is define a capturing level event handler for all the GUI events, right? And let's say the HTML tag level, right? And this means that whenever anybody clicks on anything or types on anything, it should hit that capturing level handler first, get logged, and then we should be ready to go, right? Now, it's much more complicated than that, right? Because as you know, there's DOM0 handlers, there's DOM2 handlers, right? As it turns out, on Firefox, the DOM0 handlers get called first. Okay, so you think, well, why not just register a footprints handler as a DOM0 handler? It'll get called first before any application-defined DOM2 handlers get called. We should be ready to go. But DOM0 handlers do not allow multiple registrants. So what happens if the application to log comes in and overwrites our DOM0 handler? That's not a good scene. Well, okay, you say, why not just make it a DOM2 level handler? Won't that be cool? You'd be wrong, because DOM0 handlers get called first, and they can cancel an event before it gets to the DOM2 handler. We still have to log that event because it caused at least one piece of code to run. namely the DOM0 handler that canceled it. Okay, so you might think, hey, what about getter-setter shims? Why can't I just do a get-set on the DOM0 property and then cause my stuff to run? Not going to work, right? And the reason why that's not going to work is because getter-setter shims are very fragile on all browsers. So as it turned out, I tried that, and basically what happens is that you can set the getter and setter. It'll let you set the getter and setter. It will not be invoked by the browser. You can sit there, click that button all you want, and your login handler is not going to be called. So suffice it to say, there's just a whole tale of woe behind how to get that on Firefox. I encourage you to ask me questions later on or read the paper that's on my website. We describe some of these problems. It's very tricky. Let me briefly describe why it was tricky on IE. So if you remember, I said my first pass of this solution was, okay, why don't I just have a capture level event handler that's going to take all the events before they go anywhere else and just log them, right? Well, in IE8, as you may know, there is no capture level. Right? So that solution is just done. That just doesn't work. Okay, so now you might be thinking, James, you're too pessimistic. Come on. We still have bubbling level handlers. Why not just put bubbling level handlers at the HTML tag level, then everything will eventually bubble up there, right? Won't you be fine? Answer, no. The reason why you won't be fine is because, once again, events can be canceled, right? And so an event can be canceled before it would go up to our bubbling level handler, right? Furthermore, not all events bubble. So you could be sitting up there with your bubble level handler all day. Guess what? The cows have come home. It ain't going to work out for you. So we have another solution for that kind of stuff. Once again, we can go into more detail about that later. But suffice it to say, one of the contributions of this project, we think, is sort of an enumeration of both all the types of non-determinism in a browser and also these sort of engineering level hacks that we had to engage in to get all this stuff to work. So now let me just give you a very brief example of how replay works. Like I said, stop by my demo tomorrow if you want to see this actually live and in action. So here's what the developer machine sees. So at replay time, you simply substitute logging.js for replay.js. And replay.js is going to do a couple things. First of all, it's going to put a transparent iframe on top of the application. Why is that? Because when you as the developer are replaying the application, you don't want to actually send mouse events, keyboard events to the replaying application. Because you will then cause the replayed run to diverge from the logging time run. Right? I figured that bug out the hard way. So I thought I had everything working. I was typing on stuff. Things weren't working. I was about to drop out of computer sciences, become a painter. This is important. So, got to do that. Second of all, what replay.js will do is actually interpose on all the sources of non-determinism, just like the logging infrastructure does. Except that now it's actually going to pull values out of the log instead of actually letting the underlying browser stuff do it. Third of all, replay.js will actually fetch that log, and then it's going to put up a VCR-style control. And so this control shows you things like, what's the logical clock of the event that just got dispatched? In other words, what's the event number? It's going to show you, here's what the wall clock time was during the logging run itself. It's also going to allow you to play the events in real time or quasi-real time to single-step through events. So every time you hit play, a single event is dispatched. Or we can do it in interval-spaced replay. So replay an event every 500 milliseconds, let's say. And then in that little window at the bottom, that's where you see actual information about the currently dispatched event. So in this case, we're looking at the replayed key press event, right? So we have the name of the event. The 38,0 is the character code information. The MKFFF, so modifier keys. Like when I hit a button, was shift pressed, was alt pressed, all that kind of stuff. And then we actually have the target, the DOM node target to which that key press was addressed. We need the target because that's how at replay time we synthesize these fake GUI events using fire target or things like that, right? Now, for HTML, for DOM nodes that have an explicit ID, that's how we can identify them at replay time. Now, for DOM nodes that do not have an explicit ID, which is most DOM nodes, we actually name the DOM node by its path from the root HTML element. So, if we'd had something there, like, let's say, so the current target in that example is the HTML tag. So we list it as, nothing. But let's say that it said, 1114. That would mean take the first child of the HTML tag, take the first child of that child, and then take the 14th child of the next one. And that's how we can identify DOM nodes that don't have an explicit ID. So we've done steps 1 through 3. Then finally, to replay stuff, as I just described, we dispatch the fake GUI events using the fire event or dispatch event APIs that are available in all major browsers. As we encounter timer functions in the log, we simply execute them at the time that the log indicates they should be executed. Right? At replay time, we do not let the browser itself willy-nilly fire these things off. The log tells us when we should do that. And then as the application code executes, it's going to do things like call date. It's going to do things like call math.random. And whenever it makes a call to say math.random, we should be at the point in the log where the next log entry is math.random call. So we just pull that value out of the log. So now let me just give you 2 slides of evaluation before concluding the talk. So one question you might have is, what's the performance in terms of log growth, right? Because if the memory pressure is too high, maybe the logged application starts thrashing. And also too, how much stuff do we have to transmit to the developer's machine if something goes wrong? Because if it's a whole lot of stuff and the user has to wait for a long time for this post to complete, then we're probably not going to get a whole lot of logs because users don't want to wait around. So what we show here is the log growth in kilobits per second for a variety of applications. So the first 3 are games, ranging in complexity from a fairly simple one like Tetris to Spacious, which is like a 2D shooter, kind of like Galaga, has a very high frame rate. Some dude, for whatever reason, wrote a basic interpreter in JavaScript. That guy's probably in a mental ward right now, but it's been done. Painter is just a very simple, sort of like Microsoft Paint knockoff. Nice Edit is an editor. Shell is basically an interactive JavaScript console. Long story short, I show you for each application 2 types of logs. The first one is a verbose log, which is very human readable. This is what I'll show you at the demo tomorrow. And that's merely useful for humans looking at the log trying to say what exactly took place. It looks very similar to that little info box you saw in the VCR control at replay time. But obviously that could be compressed a lot. And so the black bars that I show you are for our compact logging format. We do LZW compression in JavaScript. We actually binary pack the results to make them much smaller. So those are the log formats that you actually see in a production system. And so what we see is that in the worst case, the log growth is roughly 16, 17 kilobits per second. And that's actually quite reasonable, we think. And if it's a very long-running application, then you can actually reflect some of the log back into DOM storage if you don't want to keep it in memory, et cetera, et cetera. So this amount of log growth, I think, is actually quite reasonable. Now, the next question is, OK, you've shown me that the log growth is reasonable, but what's the CPU overhead? Right? Because essentially what we're saying is that on every JavaScript level event, we're actually going to be doing some work to log that. And so here we measure CPU overhead in terms of timer callback rates with that Spacious game, which is the most complex of all the games you looked at. And the reason, by the way, that we use games for a lot of these evaluation results is that they're actually sort of the stress test for our case. Because imagine going to like CNN, MSNBC, something like that. You're not generating that many events. You move your mouse, maybe select something, but there's like a lot of pause time. Whereas with games, you're constantly moving the mouse, you're constantly hitting the keyboard, there's a lot of timer callbacks, so games are actually a stress test for us. And so what do we see? Well, we see that in the baseline case, this is the leftmost bar, we see that Spacious is able to fire roughly 90 callbacks per second. We see that in the logging case, the performance is about 7% worse. Now, we couldn't perceive that as a user, but it's a 7% drop. But that's not actually that much. And furthermore, we can really optimize the way that we're doing string optimizations in logging.js. I mean, we're doing some fairly brain-dead stuff with concatenation and things like that. So that number could actually get much better. But suffice it to say, we think that that result's already pretty good. Right? And the key thing to note is that replay performance can be much worse than logging performance, but logging performance must be very close to baseline. Because if logging is slow and painful, users will not use this tool. Right? So if we look at the replay performance, we see that the frame rate drops by roughly 50% or so. And we're actually not that concerned about that. We can make this faster, but we actually think that that's pretty good. And the reason we think it's pretty good is because debugging is inherently sort of a slow process. So what we found is that oftentimes the way we use this tool is we sort of play forward to a certain point in time, and then we just sort of sit there and think. We look around the JavaScript debugger and we think about possible mediations. So we actually think that's pretty reasonable, right? So a 2-time slowdown for actually getting real bugs in the wild, we think is a pretty good trade-off. So now I just want to conclude the overall talk and then open it up for questions. So in conclusion, page loading is basically like defusing a bomb, right? You're always running out of time. Okay? And so one of the things that we as web developers have to do is think about different ways to make pages load very quickly. Another thing we also have to keep in mind is that failure is just persistent and chronic, right? And so I think that we've gotten into a place as sort of a web design community where people kind of accept the fact that when you surf the web and go to these complex web applications, they're always going to be throwing these exceptions. And I think that's a problem, right? I think we should actually change that. I mean, I think a lot of web applications basically almost don't work, right? And so hopefully today I've convinced you that there's some research that's being done that's trying to address both of these issues. So first of all, I talked about Silo. And Silo takes advantage of JavaScript in this new HTML5 property of DOM storage to essentially put a custom delta encoding protocol atop standard HTTP. The nice thing about this is that using that protocol, also leveraged with cookies, we can use a single HTTP round trip to fetch all of the textual-based content in a web page, HTML, CSS, and JavaScript. Right? And I showed you some results that show that even though modern web pages are very rich, are very multimedia heavy, there's still enough chunkable objects out there to make a fairly significant decrease in page load time if you use the Silo protocol. The second project that I discussed is called Footprints. Footprints is all about giving developers a better way to understand what bugs took place in the wild. So what Footprints is going to do is take advantage of JavaScript's native capabilities to introspect and reflect, and it's going to use those capabilities to capture all of the non-determinism that takes place on the client side. And so once you have that, then whenever the user encounters a problem, he or she can hit panic. A little box comes up, says, hey, do you trust whoever, Facebook, CNN, ESPN, Microsoft, to look at this log? Hit yes. Boom. That log gets shipped off to the developer. The developer can then use all the very rich local host debugging tools already built in to IE, to Firefox, to Chrome, to whatever, to actually recreate that end user's bug and sort of use that local domain knowledge the developer has on real bugs from the layperson. And so we think that's cool because, once again, English-level bug reports are often not sufficient for bug repro. But if you actually have a literal log of all the non-determinism that takes place on the client, bug repo becomes much, much easier. Once again, final plug for the demo. Come check that out tomorrow if you want to see how Footprints work. And with that, I would be glad to take any questions. Thank you. Excuse me? The question is, when is the demo? It's, I believe, tomorrow from 11 to 2. And it's in Shorelines A, I believe. Okay, so the question was, for Footprints, what do you need on the web server? So Footprints basically requires very little on the web server. The one piece of sort of trickeration I didn't discuss in the talk was how do you handle load events, and in particular things like images and stuff like that, right? Because we found out that logging and replaying loads was one of the few things we couldn't actually do just in JavaScript on the in-host, right? So for example, because the browser does not have an explicit API to the cache, the logging code can't just look in there and just grab those bits somehow and serialize them and send them back to the server. So if you care about things like logging the order and the actual bits that are returned for a particular request, then you need to have a proxy server somewhere that's essentially going to act as the logging proxy, right? And such that when the user requests something like, a.jpg, when the web server sends it back, that logging proxy says, aha, these are the bits that you, the client, saw as a.jpg at the time that you requested them. And that's tied essentially to your Footprints logging ID, if you will. And then at replay time, the replay.js will actually send requests to that logging proxy instead of to the real web server. So, but besides that, you don't need to change the server at all. Now, Silo does require a change in the server, right? So Silo does not have to have a different client, but the server does need to speak the Silo protocol. And that's actually very simple, right? So we actually hacked up a quick demonstration of this in Python. Basically, all that the server has to do is, for each high-level HTML document that a client could fetch, it just does essentially an analysis of the HTML, says, here's the inlineable stuff, right? And it constructs an inlineable version of the page, like that annotated HTML that I showed you earlier. and it also has to be able to talk to a chunk database, right? So in other words, when the JavaScript phones home and says, what are the chunks on the page, it has to be able to respond to that. Or alternatively, if you use one of those cookie-based optimizations, the server has to be able to know to look in that cookie and say, here are the chunks that the client is saying are locally available. Here are the chunks that I know are in the inline page. Let me only send back the ones that the client doesn't have. But that change is very minimal. So the question was, is it a DLL that gets attached to the pipeline? It depends on how you implement it. I mean, you could implement this as an Apache module or whatever. You could hack up your own custom web server. I mean, the protocol is agnostic as to how exactly it's implemented. So I believe you had a question over there. Okay, so the question was, can a delay in replay, so presumably because we can't do it in real time, can that mask an ordering bug in the replayed execution? Okay, that's an excellent question. So we do actually log AJAX stuff, right? So this is described in the paper in some depth. It's a bit tricky, but at a high level what we do is, much like for set timeout, how we take that user-specified callback and wrap it in login code, we take the user-specified AJAX callback, wrap that in login code too. And so we can actually see the response body in that AJAX request. That's right. And so at replay time, the replay code thinks that it's actually sending AJAX request to the network. It is not. So in fact, what it's doing is it's just sort of saying to our replay infrastructure, hey, here's a callback I'd like you to call when stuff returns. But we look in the log, and we say, this is when we know that callback should have returned. And furthermore, since we logged the response body, we say, and this is what you're going to see. So we control all that stuff. Back there. Back.
So are any of those products available to see? Because online I couldn't find any of this. Sounds like really good stuff that would be great to kind of play around with.
So all this stuff is very much sort of research prototypes right now. If you go to my research website, so my name is James Mickens, just type in James Mickens, Microsoft Research, and do your favorite search engine, and you'll find my page, and you'll see some academic papers talking about this stuff. But there's no shrink wrap product, nothing like that. We're hoping to transfer this into some product groups, but that hasn't happened yet. So I encourage you to stop by the demo, check it out. I mean, it is real, but there is no, you can't go to Office Depot and buy footprints. That, so right now you're sort of talking about my pay grade right now. So I'm a researcher. All I can say is right now, it's a research prototype, and that's the status. Yeah, we can talk about that offline or the demo or something like that.
Have you considered doing a version that's specific to like jQuery? Is that where that people make assumptions that the code doesn't say attach events directly, that your patching would be at the jQuery level? It would be a lot simpler.
Let's see. So the question was, could we integrate footprints, right, with jQuery? I'm not quite sure why you think, and would that make it simpler? So I'm not quite sure why you think it'd make it simpler.
The reason no, I think it would make it simpler is because you'd be patching jQuery, not like the native stuff to the browser. So rather than patching so you'd still have to accept
Okay.
but for click handlers, you could just patch.
Okay. So now I think I understand the question. So I believe the question is, jQuery, libraries like jQuery provide a high-level interface to some of the lower-level JavaScript nastiness. So could we? Yes. So the answer is yes, we could patch things like jQuery, assuming that everybody had buy-in to jQuery. And in fact, another thing you could think about doing is taking, let's say, Java to JavaScript compilers, C# to JavaScript compilers, and actually hooking it there, right? So that you write your stuff in a high-level language, and then we just instrument the middleware of the runtime. So the answer is yes, you could do that. And in fact, that would make a lot of the engineering hacks we had to do basically go away, because we wouldn't be dealing with it at that level. But once again, the problem is buy-in. If we could assume that everyone would access, let's say, the DOM, AJAX through our own library, yeah, trivially these problems go away. You're exactly right about that. And so in fact, if you were working in a software house where that was the case, that's the simpler thing to do, right? That's the better thing to do. But what we kind of wanted to do is say, well, what if you're just sort of your garden variety web programmer? You don't have these sort of rigorous coding solutions, things like that. All you have to do with our system is just, boom, put in login.js in every frame, and you're basically done. Thank you. Do we have a question over there? No? All right. I think we are ready. So thank you.